quick example of using Green's theorem. In class we've talked about why Green's theorem is true, and we're almost to kind of putting together a complete proof of it, and then of course the book has a rather different proof. But this is just a quick example of using it, and just a problem from the book, problem 7. So we've got the region enclosed by the parabolas, let's see, y equals x squared, x equals y squared. And so that's going to be in the first quadrant. Paint doesn't do parabolas real well, so these aren't really, they don't really look like parabolas, but it's qualitatively it's the right kind of region. Y equals x squared, x equals y squared. They meet at 1, 1. And what we're looking at is the region is in here, the orange, and we're looking at the boundary of that. Now because it's the boundary of a region, and it doesn't have any holes or anything, by definition that means C is traversed counterclockwise. And so this is the line integral around those two parabolic segments going up and around counterclockwise. Now it looks very complicated, and to set it up directly would be a pain. You'd have to split it into two pieces for the two boundary pieces. You'd have to parameterize, probably with x or y. You'd have to write down all the integrals, and you got weird stuff like e to the root x. That's not real pleasant. Cosine y squared. Those, in fact, they've set them up so that they're actually impossible integrals if you try to do them directly. But Green's theorem gives us a marvelous different way of doing this. Green's says, that the integral, there we go, over the boundary of some region, D, or they usually call it R for some reason. I like D, I'm not sure why. Of P dx plus Q dy, or in other words, the vector field Pi plus Qj integrated on this curve is equal to the double integral over D itself of what I like to call the scalar curl dq dx minus dp dy. Just the ordinary, and that's a scalar function, and we're integrating over that region. So sometimes that's not always a benefit to go from the left-hand side to the right-hand side, but very often it is. Even though this is a one-dimensional integral, it's over a random curve that has to be parametrized, and it's a vector field integral, whereas this is a scalar integral over a region, and we know how to do that. It's just an iterated integral. Might actually turn out to be harder. In this case, it won't. Okay, so here P is y plus e to the root x, Q is 2x plus cosine y squared, and right away we see that there's some red herring stuff in this problem. Anything that's in the dx, anything in P, in other words the I component of the vector field that only depends on x, will die when I take dp dy, and this stuff will die when I take dq dx. And so it's actually much, much simpler than it looks. It's actually a linear vector field case, and so that's really nice. Let me copy some of this down. And so dq dx is just going to be 2, and dp dy is just going to be 1. Hey, that's nice and simple. And so I actually just get the area of this region. If I already knew the area of that region, I'd be done. But, so let me just kill that. It's just the area of the region. But I don't really know it, but it's not hard to calculate. It's just the integral from 0 to 1, let's say in dx, and then put the dy inside. Sorry about the cough. And then from, let's see, y equals x squared is the bottom, and then y equals root x is the top. Very, very standard kind of setup. And so we're going to get integral from 0 to 1 of root x minus x squared dx, which is x to the 3 halves times 2/3 integrated minus 1/3 equals 1/3. Okay, so it's going to be, it turns out to be a very simple integral. Now this was contrived so that even though it's a complicated vector field, the part that can contribute to a circulation was a linear vector field, and the scalar curl of a linear vector field is a constant. And we saw that in our examples on the vector field analyzer 2, because, for example, the ratio of this to the area is just 1. And so that's why we just ended up calculating the area of this thing. In general, you're actually going to have a non-constant integrand right in here. But in this example, it was contrived to be simple. So we're trying to show you slightly contrived examples, but that emphasize how powerful this can be in the right situation. That something that's just, practically impossible to do directly, it becomes very, very simple.